Hey everybody, today we're going to be doing a couple things. We're going to be talking about the basically relationship between the product and the sum. We're going to be using logarithms and exponents to help us, and we're also going to find a second way to derive the general formula of the product rule, which I did find in a previous video, which I'll leave a link in the description to that. But basically this is a more intuitive way to actually find that derivative, and it's not the central focus of the video, though that's going to be a large part of it. I want to show you some really cool things about exponents and logarithms. Basically, the first property of exponents or at least one property of exponents you should know, is that e, or really any base to the a plus b, is equal to e to the a times e to the b, or again, any of those bases to the a times base to the b. This is a really cool property of exponents. Natural logs, or really any logarithm, of a times b is going to be natural log of a plus the log of b. And note that I'm going to be using the exponential function in this video. Basically, exponential of t, or base t of x, kind of works like a logarithm where it's just t to the x. It's just, this is another way of doing it where it's kind of just in one row. Exponent of e, you could say, if t is equal to e, you could say exponential base e. Oops, that's a terrible e. Exponential base e of e to the x. That's also an equivalent statement. A lot of times it's just actually just written as exponential of x is equal to e to the x. So that's those are all kind of good statements, but that's something I wanted to talk about. So it's kind of aligned with the notion of log of something, log of x. That's kind of the same, it's like a parallel form. For this video, actually, though, I'm going to be saying the exponential of a is really exponential base something. Really, it can be any base that's in the real numbers. Same thing with the logarithms. It's not log base 10, it's just log base anything. I'm not going to put the bases, though, because that's it'll add too much clutter to my formulas. So yeah, let's just get straight into it. So if you notice, well, e to the a plus b, you can actually write it as a product. This is a really cool thing about exponents. That if you raise an exponent to something, this turns addition into multiplication. And logarithms do the reverse. They turn multiplication into addition. I think that's really, really cool. So first I want to rewrite this statement. We can say, we can denote it as exponential of, f, like a function f. We can say f1 plus f2. This is actually just going to be equal to the exponential of f1 times the exponential of f2. And we can expand this to multiple inputs. We can say f1 plus f2 plus f3. And that actually looks like a sum, right? We can say that the exponent of a sum, and I'm not actually going to include the parentheses because that's kind of very cluttering also. The exponent of the sum of functions, we can say the function's I, and I'm just going to put the index here. It doesn't matter how many functions there are. It could be a finite number, it could be an infinite number. We don't really care, and I cannot write this I. We don't really care how many there are. I'm just going to include the index, all right? So the exponential base I, that's our index of our functions I. This is actually equal to the product. And I've made actually many videos including the pi product. But basically the way it works is it's just the same thing as a sum, but it's for multiplication. It's the multiplication of all our x of fi's. And again, this is index I. That's a really cool property, because from here you can derive that the sum of any function I is equal to, well, if you take the logarithm on both sides, as long as it's the same base, we can say that this is just a log of the product of our i's of, again, our exponential of our functions. And that's really cool. That's a really solid relationship between the sum and the product. Basically, the sum is just a logarithm of the product of the exponentials, which is kind of a mouthful to say, but that's a really cool property. More like foundational is the notion of our log properties. You could have like the log of A plus B plus C plus D, or in our case it would be F1 plus F2 plus F3. So we can say that the log in general, of the product, because it's going to be a product of functions, I'm going to say it's J. So if we have the product J of functions, I can say G. So the log of G sub J is going to be, well, you're going to add up all the logarithms. So it's going to be our sum of our j's of our log of g j's log of g j's. So that's a really cool property, and from here we can derive that just if we isolate this, the product of our gj's, this is going to be the exponential, because we're canceling the logarithm out, of our sums with respect to j of our log gj's. And this is more important because, the sum, if you write the sum in terms of a product, I don't know what's wrong with you, but if you write the product in terms of a sum, that's really, really helpful, because that gives us a concrete way to define a product. A product of functions, any number of functions, is just the exponential of a sum of the logarithms. So if you already know what a sum is, concretely, mathematically, you can define a product, and you can be like, okay, well, it's going to be this. So 2 times 4 is just like e to the sum of the ln of 2 plus 4. It's an easy shorthand. But really, this helps us with certain things. Basically, so I'm just going to rewrite this over here just so we can have more space to do our derivatives. So yeah, I'll just get straight into that, and I'll see you soon. Alright, so here we have, I wrote down our properties, and basically we're going to find the derivative of a product of functions with respect to x. I just kind of added that for the, it's with respect to x, that's what I'm differentiating. And so there are actually multiple ways to do this. I'm going to go over 2. I think really there are 3 ways to do this. You could use implicit differentiation as that third way, which I'm not going to go over. But the first way I'm going to go through is really just using this and kind of copy pasting this. You could just say that this is the derivative of, instead of having, because this is our gj function, that's what our fk function is, really this is just the same thing. We can just say that this is the exponential, and I'm going to use e. You can use any exponential. If you want to do it formally, you should say like, oh, exponential base k or something, but I'm just going to use e for this example. It's going to be e to the sum of our j's, or really our k's in here, of, I'll just use natural log because you have to use the same base, of our ln of gj's, or actually our fk's, fk of x. The reason why I'm using e and ln is because it's really easy to work with when you're taking derivative. So this is equal to, if we actually compute the derivative, this is equal to, well, the e to the whole thing, e to the sum of our fk's, or actually our natural log of fk's, natural log of fk's, times the derivative. But what's the derivative of a sum? Well, that's really easy because, like if you have f prime, or actually if you have the derivative of f plus g, this is equal to f prime plus g prime. It's the derivative of a sum is the sum of the derivatives. So you could actually kind of just formally say that ddx of some, I don't know, m's of fm's is equal to the sum of, or m's of fm prime. That's really straightforward there. you could make a whole proof for that, and you can actually derive that backwards, starting with the summation here. Yeah, basically if you start with these formulas, you can actually derive, actually no, it's not those formulas, it's the formula we're gonna get here. You start with the derivative of a product, and you can work your way using those formulas to that, what I just found. So that's, you know, that's cool, but that's assuming you actually know what we're trying to find now. So basically, this, because of the chain rule, we're going to multiply by that. The sum of these is going to be, you know, like the derivative of the sum is going to be the sum is the derivative of that. Basically, we're going to take our sum of our k's and we're going to find the derivative. So natural log of anything, basically we're going to have an f, yeah, because basically if you're taking ln x, derivative of that is 1 over x. So what you kind of want is on the bottom. So you're going to have a fraction, and it's going to be f of k, yeah, no, f of x, f sub k of x. And then on the top, because you're kind of doing a dx there, kind of, we're going to have the f prime of k, f sub k prime of x. That's kind of a mouthful to say. So make sure not to switch that order, because make sure that that is the order that you want. And so this is the part that we want. We remember that from the video. But what's this? Well, this is just that, right? Because, you know, with the chain rule, derivative of e to something is e to that times the inside. So that's this. But that's just that, because remember, that's what we converted. So this is simply just the pi of our k's of f sub k of x times our sum of our k's of f prime, or f sub k prime of x over our f sub k of x. And again, this also shows that you don't need the parentheses around here and here, because you can just, you know, multiply these around, because you multiplied here, you multiplied there because of the chain rule. So yeah, that's a cool way to derive it. The other way is kind of what I think of as like brute forcing it. Essentially, we're going to be using, so we're going to try to put the pi in kind of the exponential form. So you can see here that we have the log of this is equal to that. So if we say that, okay, well, f sub k is going to be the logarithm of something, we can actually use that. Actually, no, I'm sorry, the exponential, because we're using this to find like that. So if we say f sub k of x, if we let f sub k of x, f sub k of x be the exponential of a g sub k of x, and we want to use the same index, because that's just going to kind of help us and be convenient. So then all we're going to do is we're going to take the derivative of our pi, again with respect to k, of our x, of our g sub k of x. What does this do for us? Well, now this kind of just converts it into that form, right? So this is just exactly equal to the derivative of our exponential of our sum of our k's of our g sub k of x. And you're probably like, well, like, we're using a g, we just kind of came up with that from thin air. Well, this is good because, like, you know, this is kind of a u substitution, but not really. Really, it's just some substitution that we made. And this is really helping us because now all we have to do is, actually, we can just take the derivative now. Basically, we say that e, we're going to want the e, actually, I'll just keep it like that. And we can take the derivative of e to this sum k of g sub k of x. And this is kind of what we just did. This is going to be equal to e to that sum with respect to k. That's a terrible sigma, I'm sorry. Looks like a hangman, I guess. Of g sub k of x times g sub k prime of x. Okay, well, that's kind of weird because that's not really what we want, but it's okay because we can make our substitutions back. What is this? Because this is actually just that, right? And if that is that, and it's the same as that, and it's the same as that, so we just kind of, put this back in our pi form. We have pi of sub k of really just our f sub k of x, right? Because that's all the same thing, times, well, what's the derivative of g? So we can actually just kind of find it. If this is e, base e, we can say that, okay, well, we can take the natural log on both sides. We get that ln f sub k of x is equal to g sub k of x, and we just found this derivative, right? We said g sub k prime of x, that, which is what that's going to be. This is just f sub k prime of x over f sub k of x, right? Because you take the derivative with the natural log and with the dx there, basically. So this is just going to be times, hold on, something's wrong here, because we can't just have this like that. Oh yeah, I forgot to include the sum here. Yeah, because we're including the sum with our k's. There we go. So then this is the sum of our k's of, again, just f sub k prime of x over f sub k of x. So yeah, those are two ways you can do it. You can also use implicit differentiation, which is pretty similar to the first method, so I'm not going to cover that. You can if you want. But yeah, this is just such, this is so cool. I never realized these little, relationships. These I always knew since, algebra 1 or 2, I forget. These I knew for a while, but, to think, okay, well, you can generalize this using your sums and your pi's, and to come up with these cool formulas, and they look cool, too. It's like, wow, you have this log of the pi's or the g sub j's, and, it just looks fancy, and it's really actually very simple. It's just a relationship between addition and multiplication. That's literally what it is. And you can come up with the pi, the generalized product rule of the derivative. You can come up with so many things. So yeah, that's basically it. Thank you for watching, and I'll see you in the next episode.